and the top terminal of PMOS will be connected to supply, the bottom terminal of the NMOS will be connected to ground. So this will become source of the NMOS, that VDD will become source of the PMOS, and the middle terminal will be our drain terminal for both NMOS and PMOS. And their gate terminals are tied together, and input voltage is applied to that input terminal. It's a single input, single output terminal. So the voltages for NMOS will be VGS of N, gate voltage of this NMOS transistor. On the other hand, from the top, source gate voltage will be between that terminal plus at the upper side minus at the gate side. And then the output will be with respect to this terminal and ground. So, but in this circuit, there are two sets of voltage and we have to find relation between them. One set of voltage, they are related to each individual transistor. Each individual transistor will have a gate source voltage, drain source voltage, right? Or source gate voltage and source drain voltage. And then as a whole, the whole inverter has an input and output. Now we want to relate voltages of the inverter, how they are related with the voltages of individual transistors. The way the voltage polarities are assigned, input voltage is with respect to this terminal and ground. And gate source voltage of this NMOS is also with respect to this terminal and ground. So for a CMOS inverter, input voltage is actually equal to gate source voltage of the NMOS. On the other hand, for the PMOS transistor, its source gate voltage is equal to VDD minus input. Source gate voltage of PMOS, V as G of P, is equal to VDD minus input. Now let us look at this one. Output voltage is measured with respect to this terminal and ground. Drain source voltage of this NMOS is also measured with respect to this terminal and ground. So the output voltage of a CMOS inverter is actually equal to the drain source voltage of the NMOS. On the other hand, source drain voltage of the PMOS will be VDD minus Vout. So you have to know this terminal relation before we can talk about the voltage transfer characteristics. So now, input voltage, let's say we are talking about a particular CMOS inverter that is operating with a 2.5 volt supply. So your input can go from 0 to maximum 2.5. Your output can also go from 0 to maximum 2.5. Let's say it has a threshold voltage of 0.5 volt. So initially it will increase, still the transistor is considered a low input. So for a low input, as input voltage increases, output voltage will not change. For low input, output voltage will remain constant. But further increase of input voltage, here in this area, it is still below threshold voltage of the NMOS. So NMOS will be in off state, PMOS will be linear or resistive state. But as we further increase the input voltage beyond 0.5, gradually PMOS will remain on, but NMOS will also turn on because it is above threshold voltage. From this point to this point, NMOS will gradually enter from linear to saturation region because we are increasing this voltage. Our NMOS will turn on, but it will turn on in the saturation region. So in this point, both NMOS and PMOS will be on in saturation region. Further increase of, NMOS will be in saturation, PMOS will be still in linear region, but it will gradually enter into saturation region. Further increase, we will reach the midpoint of voltage transfer characteristics when, if you test the condition, both NMOS and PMOS will be at the saturation region and both transistors will be on. This is the midpoint of the voltage transfer characteristics. If we increase it further, at this point, NMOS will enter into linear, PMOS will remain in saturation, but both will be on. But further increase of input voltage will turn off the PMOS, because it will turn off, because it is not very good pull down device, it will turn off at one threshold voltage above ground. NMOS will enter into linear and it will take the output voltage all the way down to 0. So here, at this point, PMOS is off and MOS is in linear region. So we have five important points in this voltage transfer characteristics or region. Here, for very low input, NMOS is off, PMOS is on in the linear region. One of them is on. Here, NMOS is linear, PMOS is off when input reaches the final value here, or the very close to VDD. In between these 3 points, both transistors are on. So the ideal characteristics says that up to here, one transistor is on, the other will be off, so it will make a perfect level. For this range, one will be on, the other will be off, so it will make a perfect low level. So it is now deviated that here NMOS and PMOS will be turned on and off instantaneously following a perpendicular path. If this turns on, this will be on. But now we see that there is a finite region during the transition when both transistors will remain on. As a result, we will not have this type of rectangular curve. We will have a gradually decaying curve, and then it will sharply decrease during the transition, and then it will gradually go towards 0, not sharply perpendicularly go to 0. So this is the real voltage transfer characteristics, which shows us that initially NMOS will be off, PMOS will be on. In the last part, PMOS will be off, NMOS will be on. In between, both will be on. However, for one, current will go up, the other one, current will go down. So as we are making a forward transition, NMOS current must go up or remain at saturation to bring it down. PMOS current must go down so that it can decrease. So each of these points which limits the beginning or end of another region of operation has a name, has a huge significance or impact in inverter behavior, and we will talk about it. So now the question is, I'm just saying you that here NMOS is off, PMOS is on, here one is in saturation, one is in linear. I want you to write down all the linear and saturation condition for each of the 2 transistors in this inverter and check the condition by yourself to make your concept clear. For each individual transistor, you have to test that. Yes.
So if this is an inverter, and I'm looking at the plot, both voltages are positive. Shouldn't one be the negative of the other?
No. As input is going up, x-axis is input curve. As input is going up, output is going down. This is the direction. If you decrease the input, output will go up in this direction. So it is actually inverter is going the other way. So buffer is a different thing. In case of buffer, if input goes up, output also will go up. So it will be like something like this curve. If you look at this curve, it's an inverted curve. So now, let us define those 5 points which we mentioned. At the beginning, when output is perfectly at 0, input is 0, we will have a perfect output because it's a CMOS inverter, full voltage swing, output high will be perfectly equal to VDD. For some logic circuit, output high will not be equal to VDD. But our first point of interest is VOH, which is the output high. The second point of interest is V input low. Up to what value above 0, input will be considered as low input. It's a range of input when it will be considered as a low input for which we should get a high output. The third point of interest is VOL, V output low. Fourth point of interest should be then V input high. What is the minimum voltage above which input should be considered as a high input, for which output should be low? And then we introduce a transition point, midpoint of the voltage. The transition, during the transition, the midpoint of the switching threshold voltage, this voltage transfer characteristics when both transistor enters into saturation region. Before that, NMOS is saturation, PMOS is linear. After that, NMOS is linear, PMOS is saturation. At this point, both are in saturation. This is called switching threshold voltage of inverter or logic gate. We have to make difference. Each transistor has its own transistor threshold voltage to turn it on. Switching threshold voltage is a parameter in the voltage transfer characteristics of any logic circuit. It is the midpoint of the voltage transfer current transition. And that the symbol for this is VM. VM. VM is the midpoint, switching threshold midpoint of the transition. So now, for CMOS inverter, because it's a full voltage swing, for CMOS inverter or any steady CMOS circuit, it can always produce V output high equal to perfect VDD. For CMOS inverter, it's a steady CMOS. We use NMOS for pull down, it's a perfect pull down, so it can produce a perfect binary 0. However, input low is a range of voltage from 0 to certain positive voltage. Within this range, if the input signal falls into this range, then it will be considered as a valid input low. Input high is certain positive voltage from there to VDD, the maximum input voltage. If input voltage falls into this range, then it is considered as input high.
So that's a VE, is that a VE?
VIH.
Yeah, VIH.
This is a positive voltage above the midpoint. Because it's input high, it should be close to VDD. So it's a positive voltage slightly below VDD. From there to VDD, that range is input high. And VM, so V input output high, V input low, V output low, V input high, and VM. So now, as you can see, in our voltage transfer characteristics, curve is going down like this. Why? Because we have NMOS transistor and PMOS transistor. Through the NMOS transistor, let's say this is my output. IN, or current through NMOS, is discharging. Current through PMOS, it is charging the output node. For a downward discharging, this has to be greater than this one. But initially, when NMOS is off, this current is small, and this current is larger. That's why it is remaining at high value. Gradually, this is becoming stronger. This is becoming weak from 0 all the way to VDD. In some other logic circuit, we will see that VOH will be less than VDD, or VOL will be greater than 0. So this VOL, VL will be a fraction of VDD, maybe 0.9 VDD, 0.95 VDD. And those are not full swing logic. So logic swing or voltage swing for CMOS inverter is equal to VDD. That's why it is called full voltage swing or full rail output. Now, input low and input high, we already defined its qualitative definition. This is the maximum value of input, which will be considered as low input. This is the minimum value of input, which will be considered as high input. Up to this, it's input low. At this and above will be input high. And we also, from graphically, we know that input low, VIL, is the input voltage corresponding to point A. VIH is the input voltage corresponding to point V in the voltage transfer curve. And mathematically, it is observed that what is this curve? It is a change of output with respect to input, right? And when input is going up, output is going down. So this curve will have what? A negative slope. Slope is dvy over dx, right? Change in the y direction with respect to change in the x direction. That is the slope. So it is observed that mathematically at point A and at point B, the slope of this voltage transfer characteristics dV out over dV in will be equal to -1. So we got another mathematical definition of VIL and VIH. At point A, the slope of these voltage transfer characteristics will be -1. And also at point B, the slope of this curve will be -1. And the first one, input voltage corresponding to A is called VIL. And the second one, the input voltage corresponding to point B is called VIH. So any signal falling between VIH and VIL, if any input signal falls in this region, then it will be an undefined input because we call it forbidden region. An input cannot be in this range because in this range it will not be considered as low input or it will not be considered as high input. And that leads to our another definition, transition width of the logic signal, which is the VIH minus VIL. This is the forbidden region or transition width, the distance between valid logic 0 and valid logic 1 input. That gap in between is the transition between two valid logic. So, and any practical logic circuit will have a finite transition width. But if our voltage transfer characteristics is ideal like that, VIL and VIH will fall into each other, right? It will be the same thing. So the transition width will be 0 in case of ideal. So if you, now let me compare with ideal. If you have a near perfect voltage transfer characteristics, this transition width will be smaller because then VIL and VIH will be closer. But if you have a very distorted voltage transfer characteristics, something like that, your transition width will be much wider. That means you will have a much shorter range of village 1 and much shorter range of village 0. And in between, there will be a much wider range of voltage input which will not be considered as a useful or meaningful input. So there are pros and cons in having a shorter transition width versus a wider transition width.
So I'm sorry, so what makes it 4 meter range, like you said?
Because from VIL to VIH, within this range, it is not considered as varied input low or varied input high. So if your input signal falls into this range, then your logic circuit will not be able to produce any meaningful output. Because logic circuit first it has to recognize whether it's a low input or high input. Then it will produce a corresponding output. So for the logic circuit to recognize it as a 0 or low input, the input voltage must be in the range 0 to VIL. For the logic circuit to recognize it as a high input, the input voltage must be VIH or greater up to VDD. So in between VIH and VIL, that input range is where the input will be meaningless. And in the voltage transfer characteristics, that's the transition region. In the transition region, we do not evaluate logic output. We take only logic output from here or here. Yes.
And I was just going to say, that's the state where they're both on at the same time.
Yeah, both are on, so it's just making transition. So between VIH and VIL, that's called transition width. During the transition, why it is called transition width? Because the logic circuit is making a transition either from 1 to 0 or 0 to 1, depending on which direction input is going. And during this transition, we do not evaluate the output. We wait for the transition to finish. Then we evaluate the output. And during that range, the input is meaningless. And that is also known as the dynamic behavior range for any logic circuit when it is making an upward or downward connection. So now let us look at, so the switching threshold voltage Vm is the midpoint. There is another way to define it. Input is going up, right? Output is going down. Initially output was at VDD. Input was at 0. Input is moving towards VDD. Output is moving from VDD towards 0. At one point they will cross each other. That crossing point is VM, switching threshold voltage. Now, can you say that that crossing point will be exactly at half VDD? No. Because input can go up at a much slower rate than output. So they can meet above half VDD or below VDD. But if the change, the NMOS discharging and PMOS charging, they are equal, if you can do the sizing of the NMOS transistor to make their resistance equal, so the discharging and charging will be symmetrical, then VM will fall exactly at the midpoint, half VDD. So there is a midpoint of the transfer characteristics and there is a midpoint of the voltage. Midpoint of the voltage is half VDD because input is going from 0 to VDD, midpoint is half VDD. Output is going from VDD to 0, midpoint is half VDD. But as input and output is going up and down, this side of the slope and this side of the slope, if they are not identical, they will not meet at half, they will meet. That meeting point, that corresponding voltage, when input becomes equal to output, that voltage I am calling it switching threshold voltage VM. The question is whether that will be half VDD or not. That depends on the symmetry of the NMOS and PMOS transistor. So you as the designer, one of the design target for you will be to make VM equal to half VDD by selecting the proper size of the transistor, so that for this transition and this transition it takes equal amount of time and they meet right at the midpoint of the voltage, half VDD. So now let us look at the different switching scenario for the CMOS inverter. If input is 0, we know that NMOS is off, PMOS is on, and PMOS we know that can take the output all the way up to VDD. So VOH will be equal to VDD. If input is high, NMOS is on, PMOS is off, and we know that NMOS is good pull down, so output will go all the way down to 0. So our VOL will be perfect 0. And we have to do some very complex derivation and mathematics to actually calculate VIL and VIH. This will be very, very time consuming, multi-step. I will give you a practice problem for you to practice probably in a quiz or exam. You cannot finish it because solving for VIL, VIH, each will take like 30 minutes each. I will show you the step by step how to calculate VIL and VIH for a simple CMOS inverter. But I want you to practice just to make your concept clear, the design steps. So inverter switching threshold voltage, as I mentioned, VM. This is when input and output is equal to each other. And if that VM falls at half VDD, then we call it symmetrical inverter. So, as I said, we have to do step by step for CMOS inverter. So now let us summarize. For CMOS inverter, 5 of the most important voltage parameters are VOH, VIL, VOL, VIH, and VM. By default, for any CMOS static logic circuit, including inverter, we know it is VDD, nothing to calculate. By default, it is equal to 0. We have to calculate this one, and this one. Somewhere in the problem statement, if you see the word symmetry, so you don't have to calculate anything. By default, you know it is
VDD by 2.
half VDD. For a symmetrical inverter, you don't have to calculate VM, because by definition, by the condition of symmetry is that VM should be half VDD. So if you get any design problem, for including any CMOS inverter or any CMOS static logic circuit, and if you are asked to calculate VM, first see whether it is somewhere it is mentioned that it is symmetrical logic gate. Then you use, or later in the later slide we will see to check some condition before solving the problem. If the conditions are met, then it is symmetrical inverter, then straightforward I can write VM equal to half VDD. Otherwise we have to go through long derivation and solution for VM, VIH and VIH. So we'll focus on that. This is the problem we will discuss in class, next class after the quiz. Next class, the TA will be here. He will conduct the quiz for 30-35 minutes. It will be a little bit longer quiz from lecture 2. Lots of questions on MOSFET. And then,
Any
yes.
mathematical equation or mathematical problem?
If you have to use the linear or saturation current equation, those equations will be given in the question. Behind the question, there will be a cheat sheet printed for you. But you have to know what are the conditions for linear saturation curve. That is a conceptual issue. But I don't want you to memorize a complex quadratic equation, linear or saturation current equation at this point. Over the time, it should get into your head. But at this point, there will be a cheat sheet on the back side of the question if you need to use any equation. If that equation is not given, that means you are missing something. You should be able to solve the problem without that equation. So I'll just tell you, this is the exact problem the TA will discuss in a class. So now, we introduce 5 important voltage parameters for CMOS inverter or any static CMOS circuit. Now let us introduce 2 other important performance or reliability parameter for any logic circuit, including CMOS inverter. And these are called noise margin high and noise margin low. For any electrical or electronic circuit, what you are doing? You are processing a bunch of electrical signal, right? Whether it's an analog signal and a digital signal. Every signal will have a desired value. If any disturbance, electrical disturbance, deviates that signal from its desired expected value, what we call it? Noise, right? Any distortion or disturbance of the signal level is considered as a noise. So, one of the biggest threat for any electrical or electronic circuit is the noise. So, how do we measure the robustness of any electronic circuit or electrical circuit? We measure it robustness in terms of its ability to tolerate noise or eliminate noise. There are 2 different things, noise margin and noise immunity. Noise margin means what is the maximum amount of noise it can tolerate without having the signal flipped or go into undefined region or having an error, right? So that's called noise margin. Noise margin is by definition is the maximum amount of noise a circuit can tolerate before it gives an erroneous signal. On the other hand, noise immunity means ability of a circuit not to be bothered by a noise. Because there are some types of noise which cannot affect a digital circuit, because these are not relevant to digital circuit. There are some type of noise, those are not relevant to analog circuit. So, or you can make a circuit in a way that no matter what is the magnitude of noise, the circuit is immune to that type of noise. There are many different types of, that is called noise immunity. Noise immunity means irrespective of magnitudes and directions and phase of any noise, if that particular noise cannot affect the circuit, then we say that the circuit is immune to that type of noise. That is called immunity. But if a noise can affect a particular circuit, relevant to a particular circuit, what is the maximum range it can tolerate before it can give some noise? It's an error, signal error, that's called noise margin. In case of digital circuit, CMOS inverter, we have 2 signal range we are concerned. One is input output high, one is input output low. But we have to pair them. For a maximum input low, we want a corresponding high output. And then for an input voltage minimum and above, we want to consider it as high input and corresponding output should be low, right? So at the lower range of the voltage and at the upper range of the voltage, there are two varied range here and here, where we consider that the signals are varied. Outside this range during the transition width, the signals are not varied, it's undefined region. So now I am drawing the signal level in a different way. At the top of the curve, the maximum VOH can be what? VDD. Or it can be less than VDD. And then VIH, the minimum input high is a voltage close to VDD. And then perfect VOL is 0. VIL is a voltage above 0. So this shaded region is where we will take a signal as a varied signal. That shaded region and the higher side, we will take it as a signal as a varied signal. Outside the region, we are not going to evaluate into output. So this is called noise margin low. That is called noise margin high. The difference between VOH and VIH is the noise margin high. My input and output must be in that range for it to be considered as input high or input low. Below that, it is an undefined signal. Similarly, for input low and output low, both has to be in this range to be considered as varied input low or input high. Sorry, input low and output low. That is called noise margin low. So by definition, noise margin low is the difference between VIL minus VOL. For CMOS inverter, VOL is 0, so noise margin low is equal to VIL. By definition, noise margin high is the difference between VOH minus VIH. By default, in case of CMOS inverter, this is VDD. So noise margin high is VDD minus VIH. But for general purpose logic circuit, it is the noise margin low is the difference between VIL and VOL. Noise margin high is the difference between VOH and VIH. So you see, noise margin is a dependent parameter, dependent on 5 unique voltage parameter we talked about earlier. So every single performance parameter we are going to discuss later will be determined by those voltage parameter we introduced in the voltage transfer characteristics. Transition width, as we mentioned earlier, is that white gap area, the difference between VIH and VIL. Ideally, if we think about the quality of input and output signal or the availability of input and output range or varied voltage range, we want this transition width to be as small as possible. So this gap, if this gap is smaller, there will be a longer range of input voltage which will be considered as very low. There will be a longer range of output high which will be considered as valid output high, right? So transition width it is good to have a smaller transition width. However, there is a problem. If the transition width is too narrow and you want to maintain an input low voltage, right? And the noise is injected, a positive noise is injected, which can increase your input low voltage and push it to the undefined region or push it to the high region where you actually meant to apply a low voltage. So the noise can push the voltage inadvertently from low side to high side and high side to low side if the gap between the very low range and very high range is too narrow. So from noise robustness point of view, having too narrow or shorter transition width makes the circuit vulnerable because then it can flip with unintentional noise from one side to the other. On the other hand, having a too wide transition width means that your valid 0 range and valid 1 range is now too narrow, right? So there is a trade-off. Now, up until this point, we are only considering the static behavior or steady state behavior. When input is low, output is high, input is low, vice versa. At different points of input steady state point, what will be the voltage parameter? But now let us look at the behavior during the transition when both transistors are on. And that behavior is called dynamic behavior or transitional behavior of any logic circuit. So, that behavior during the transition region, as I said, is known as dynamic behavior of any logic inverter, and that behavior will determine propagation delay and transition time of any logic circuit. So these are the two timing parameters of any logic circuit. So now I am introducing fourth set of parameters, performance parameters for any logic circuit. First we introduce a set of 5 voltage parameters, defining different points in the voltage transfer characteristics. Then we introduce noise margin, 2 noise margin that will define the robustness of the circuit, how robust they are against any noise disturbance. Now we are introducing third sets of parameters that will define the timing, the speed of your logic circuit. First we define the signals, high and lows, and their limit. Then we define the robustness parameter, noise margin. Now we are introducing the timing parameters that will determine the speed or frequency of your circuit. And those timing parameters will be defined or will be present, will be relevant during the transition time or the dynamic range, and the behavior is called dynamic behavior. So let's start with the timing parameters. There are 2 types of timing parameters in any logic circuit. One is called propagation delay, the other one is called transition time. Propagation delay is a relative timing measurement. Transition time is an individual timing measurement. It will be clear. So now, let me define with respect to the inverter. So once again, what we said, propagation delay is the relative timing parameter. It defines how much time it takes for an inverter or any logic circuit to make a change at the output with respect to a certain input. That means it is the time difference between application of the input and the availability of the output. It cannot take place instantaneously. You have to apply certain input, the circuit will make some transition up, down, and then after a certain point when charging of this or discharging of this output capacitance is done, your output will be available, 1 or 0. Between these two phenomena, application of the input or injection of the input and availability of the output at its desired level, there is a time difference. That is called signal propagation delay. The time it takes for the signal to travel from the input terminal to the output terminal to change the output to its desired value with response to the input. That's called propagation delay of any signal through any electrical or electronic circuit. So the timing is a relative measurement from output to input. When a stable output is available, you subtract when a stable input is applied. That timing is called propagation delay. Now what is transition time? Let's say you want to apply a high input here. That means the input itself is making a 0 to 1 transition. That input, ideally, an ideal signal can go up like this, 0 to VDD, if you are applying a high input. Practically, it cannot happen like that. Practically, an input signal will go like this, from 0, after a certain time it will VDD. So before even the circuit can register that a high input has arrived, the input has to go up to the high level, right? So this time it takes to be raised from 0 to VDD, it is not instantaneous. It has a finite time. It's called transition time. If it is rising, it's called rise time. If I have a falling input signal from VDD to 0, this transition is called fall time. That's why, as you can see, there are two transition times. One is rise time, one is fall time. So transition times are related to each individual signals. How much time? Same thing for output. When you have an input high, output should go low. But discharging of that output capacitor takes certain time. So output will take certain time to transit from high to low. So that time, each individual signal, the time it takes to go up and down, irrespective of what is happening in the rest of the circuit, that is the transition time of each individual signal. In digital circuit, each signal can go up, so there will be a rise time. Each signal input or output, irrespective of where they are, it will take certain time. Falling, it's called fall time. So the dynamic behavior of inverter will define or determine these two timing parameters, propagation delay and transition time. There can be rise time and fall time when we talk about transition time. So now, you as an engineer, you have to propagation delay is a measurement of time difference between output and the input. Transition time is the measurement of time difference from the beginning to the end of the signal transition. But you have to have two valid reference points in time scale to do the calculation, right? Now in the definition, we are going to introduce the definition of actual calculation of propagation delay and transition time. So now let's talk about propagation delay. Let's say your input is going from 0 to VDD, 0 to 1. Correspondingly, it's an inverter. Output will go from high to low, VDD to 0. The question is, now as you can see, the output starts going down after some time. It does not start going down when input is applied. Now as you can see, we have to measure the time difference between input and output. Where do we do the measurement? What will be the two reference points? If both signals are ideal and symmetrical, it will not be a matter. We can take the initial point of the input when it starts going up and the initial point of the output when it starts going down. The time difference is our propagation delay. Or the final destination of the input VDD and the final destination of the output 0. If we take those two timestamps, that difference should be our propagation delay, right? Difference between the initial values of input and output, or difference between initial values of input and final values of input or output should be our propagation delay. Assuming that it's a perfectly symmetrical signals going up and down exactly in the same rate, no oscillation. Practically, for any electrical signal, it is impossible to determine which exactly the actual initial point, because as it is going up, it is not going up smoothly. It is going up while oscillating. It is going down while oscillating. So if you put these signals in a high power oscilloscope, you will see that there will be 10 different initial points because they are oscillating at the beginning, they are oscillating as it's going up, they are oscillating. It will never have a final rest. It will go up and down against VDD. So in a real life, it is very difficult to define the initial point and the final point for any signal because there is no initial point. It is always oscillating, even if it is going up and down. So that's why in logic circuit or in most of the electrical circuit, it is standard practice to get the time stamp when input reaches the first time reaches the 50% point, and the second time stamp to be the 50% point of the output. That time difference is called propagation delay. For an ideal signal, it should not matter, right? If they start and rising and falling exactly at the same time, if we can define initial point and the final point clearly, perfectly, then there should not be a problem. But because it is very difficult to define starting point and the end point for any electrical signal, it is a standard practice to take the 50% point of the input signal and the 50% point of the output signal as the two time references to calculate propagation delay. So what we are going to summarize, propagation delay for any logic circuit is the time difference between 50% point of the output and 50% point of the input. So propagation delay is equal to the time at 50% point of the output minus the time at 50% point of the input, because input starts changing earlier. Similarly, since rise time ideally should be the time it takes to be raised from 0 to VDD, ideally fall time should be the time it takes to be lowered from VDD to 0. But practically, there is no finite beginning time, there is no finite end time. Because against, even when it is low, it is oscillating, even when it is high, it is oscillating. So it is very difficult to clearly define rise time and fall time if we take as the final initial point and the final point as the reference. So it is standard practice to take 10% point, that means if it is rising, when it reaches 0.1 VDD and input is going, and up to when it reaches 0.9 VDD. This difference is called rise time. Similarly, when it is falling, first point is when it is 0.9 VDD, from there to 0.1 VDD, I'm talking about the output. So that's called fall time. So the reference point for fall time and rise time calculation is the 10% point and the 90% point. The difference is transition time or rise time and fall time. So now, as you can see from this graph, in one scenario, there will be one propagation delay when output is going down, making a high to low transition. Then the propagation delay will be 50%, this 50% point and this 50% point. There will be another scenario when output will be going from low to high, correspondingly input will be going from high to low. So there will be one propagation delay for high to low transition of the output. There will be one propagation delay for low to high transition of the output. If your logic gate is symmetrical, they should be equal to each other. Symmetrical means all the transition will be at same slope, same time. So both side difference will be same. But practically, it is difficult to maintain symmetric condition at all condition. So practically the propagation delay for any logic circuit is the average of low to high and high to low propagation delay. And Rise time and fall time, as I defined, it is the time difference between 90% point and the 10% point. Time at 90% point minus time at 10% point for rise time. For fall time, it's opposite.
Do we still use that average value for asymmetric inverters, or is it just the point is to avoid?
Typically in data sheet, all the values are given. These are all the average value. Practically, even if you make the logic circuit symmetrical at the beginning, depending on the signal combination, for 90% of the case, they will not behave as a symmetrical. Even if you apply all the design technique, the gate will behave as a symmetrical logic gate only for a small subset of logic combination. If you have a 4-input logic gate, you are talking about 16 combinations of input signal. Out of 16, probably for 2 or 3, maximum 4 combination will give you a symmetric behavior. So now, let us now relate with the earlier switching behavior, the switch model diagram we drew for inverter to the propagation delay or the speed or the timing. Now, when output is making a low to high transition, that means we are charging the output node. That means our PMOS is on, NMOS is off. That means input is low. When input is low, NMOS is off, PMOS is on, output is making a low to high transition. And that time will depend on this resistance and this load capacitance. So the TPLH, propagation delay low to high for any CMOS circuit, will be a function of ohm resistance of PMOS and the load capacitance. Similarly, input is high, output is making a high to low transition. So the propagation delay high to low will be a function of NMOS ohm resistance and load capacitance. So from these two equations, now you know what to do to make it symmetrical. Symmetry means these two propagation delay must be equal to each other. Inside those, CL and CL are equal. So what do you have to make? To make a symmetrical inverter, you have to make sure that equivalent ohm resistance of PMOS is exactly equal to equivalent ohm resistance of NMOS. If you make them equal, your TP LH will be equal to TPHL, and it will be a symmetrical inverter or symmetrical logic circuit, right? So this now let's now introduce this derivation. I'm going to show you step by step kind of an approximate derivation of propagation delay high to low, and then it will be similar. You don't have to do this type of derivation, but this derivation will show you how performance parameters, propagation delay high to low and low to high, they are dependent on the voltage parameter as well as the transistor's device parameter. But now, let me go back to the voltage transfer characteristics. So if you ask me, what is the most important thing in CMOS inverter lecture? As I mentioned again and again, for this entire course, lecture 2 and 3 will be the most important lecture. And in lecture 2, we identified few slides. We identified few slides about MOSFET that will be very, very important. So in CMOS inverter, if you can understand why and how different parameters in voltage transfer characteristics are defined and how they are related to each other, from slide number 14 to this slide 20. Initially, these 7 or 8 slides, if you can basically understand very clearly that all the details of voltage transfer characteristics and definition and relation of voltage parameters with performance parameters, then your understanding about CMOS logic gate design and operation will be very clear. So, for any interview questions from this lecture, those slides will be 14 to this 36. But within this 14 to 36, spend a lot of time on 14 to 20 just to learn the basics of voltage transfer characteristics. So, those who did not take any logic circuit or any kind of digital design circuit course, it will be a little bit confusing. But I want to spend as much time as possible on this lecture 2 and 3 before we move forward with rest of the lectures, because you will be handicapped in this area if you do not understand the contents of these 2 lectures. So that's all for today. I don't want to add more, but please spend time on this. So starting from not this Thursday I will be most likely either coming late in the class or I may skip the class. TA will solve that inverter problem showing the slide, and also at the beginning he will take the quiz. But starting from next Tuesday, 1 p.m. to 2:15 p.m. every Tuesday is open for anyone in this class. You can just walk in, no prior appointment needed. 1 p.m. to 15 p.m. every Tuesday. Any questions regarding this class? I want you to come to my office to discuss any confusion you have or ask me a question in the class. Okay? So this is actually a very good time to be in microelectronics industry, and there will be lots of changes, not only from technological point of view, also from geopolitical point of view, for this type of area track. I know some of you have heard that America is desperately looking for an alternative location for some of its chip manufacturing plant. Full manufacturing plant probably will not be possible, but they are looking at least